Hello everyone, welcome to the channel. So in this video, we are going to code linear regression from scratch. So before starting the coding part, let us see the mathematical equations that are involved in linear regression. So we basically have five main equations. One is the hypothesis, next is the error, another thing is the cost function, next is the gradients, and finally the gradient update rule. So these are the five main equations that we need to know of. So first I will explain hypothesis. So hypothesis is the y hat equal to x dot w plus b. So y hat is the predicted output value, x is the input vector, w is the weight vector, b is the bias. So error is nothing but the difference between the predicted vector y and the actual output value y. Okay, one thing to I will also explain this how the input vector is structured. So what makes up the rows and what makes up the columns? Suppose we have a housing data set. So here is an example for that. So here the each row represents a unique house. You can see here like first row represents house 1, second row house 2, third row house 3 and so on. And each column represents the feature vector. So this is very important to remember. So as a beginner, this will be very hard to visualize like what is the rows, what are the columns. So you just understand each row represents a data point. Okay, now let us move on to cost function. So we need some kind of mechanism to determine if the model is performing well. So it is also known as a loss function. In regression models, we usually use mean squared error. So as the name suggests, you can see we are squaring the error and finding the mean. So the formula you can see that is done here. So the y hat minus y vector. So this is the error and we are squaring it, and we finally find the mean of it. So what we basically are doing is that we are finding the predicted value for each row and then finding the average across the columns. So there are five houses. So we will find the error for each row and divide it by 5. So that is the loss function. Next is the gradient. Gradient shows the direction in which we have to move to reach the global minima. So the loss function in linear regression is a convex function. So we actually have a global minima. So we need to know in which direction we need to move to get to the global minima. That is determined by the gradients. So this is the formula for gradients. The derivation from cost function to the gradients is very important, but I'm not going to explain here. You just refer some online resources, but that is very important to actually understand how linear regression works. So you can see in this in the formula, we are actually transposing x and multiplying it with the error and then finding the average. So same is for bias. There is the bias is simply a column vector of just filled with 1, that is actually bias. So you are basically multiplying 1 into error, so that's why there is no x value here. Next is the gradient update rule. So we have found the gradients, we have found the direction in which we have to move, so we have to update the weight by moving towards the global minima. That is what is being done here. We have to multiply the gradients with a learning rate and then subtract it with the weights. So this shows that we are moving down towards the global minima. Same is for bias. Okay, now another important thing is that for linear regression, we actually don't need to use gradient descent rule at all. There is another closed form equation where we can just find the weights using a simple equation. We will also code that in the second part. Okay, now let us move on to the coding part. Okay, now we can start the coding process. First, let us import numpy. We will create a class for linear regression. In linear regression class, we will have three methods: init, fit, predict. In init, we will pass the parameters that we need to create pass while creating the object, such as learning rate and the number of iteration. So learning rate, okay, we can just keep it as alpha. number of iterations. Okay, in predict method we will pass the training data set, which is the input vector x and the actual output value is y. In predict method we will pass the input vector for which we need to predict the output values. So we will assign class variables alpha equal to alpha, iterations equal to iterations, weights equal to none, bias equal to none. So why are we assigning none to weights and bias? Because the length of the weights is equal to the length of the feature vectors in input vector. So unless you know the actual input vector, we can't assign the weights held. So only when you get the input vector, we will create the initialization for weights and bias. Fit self y. So now let us find the shape of x. So as I already explained, the rows represents the number of data points and the column represents the feature vector. So the rows represents the number of data point, the column represents number of features. Also the weights equal to np dot zeros, weights equal to number of features. Bias is a scalar value, so we can just assign 0 for now. So unlike neural network and deep learning, we can assign zeros for weights and bias in linear regression, but you need to be careful when assigning weights for deep learning. Okay, now we have to create a loop over the number of iteration. So this is the gradient descent code. So we have to do the gradient descent for the given iterations. Okay, now we basically have to code the mathematical equations that I explained earlier. First is the forward pass. So predicted y equal to x dot w. So it is a dot multiplication. So x is the input vector, weights is the self dot weights plus self dot bias. So next is the error. So error equal to predicted y minus actual y. So actually we don't need to code loss, because as you can see the parameter j is never actually used in finding the gradients, or nor it is used in the gradient descent rule. So we don't need to calculate the loss. So gradients equal to, so we have to do dot multiplication after transposing input vector x with the error. So np dot x dot t error and divide by the number of instances. So in bias, we just need to sum the error and divide by the number of instances. So np dot sum error and divide by the number of instances. Okay, next is the update rule. So self dot weights equal to self dot weights gradient update. So self dot weights equal to self dot weights minus alpha into gradients. So similarly for bias, self dot bias minus alpha into gradients of bias. Okay, I said we don't need to calculate loss for the gradient descent, but calculating loss helps in finding if our model performs well. So just for learning purpose, I am also going to include the loss. So we can include the loss after the error. J equal to np dot mean error square. So we will just print the loss for every 100th iteration. Print loss at ith iteration is loss. So for every 100th iteration, we will get the loss of the model, so that you can see how the loss is getting reduced as you train the training data set. Okay, now you have found the updated weights and the bias. So next is the predict method, self x. So here you will only receive the input vector x, and we have to return the predicted output value. So return. So basically we have to return the forward pass. So we have already coded the forward pass, so we're returning it. So this is the basic linear regression with a normal gradient descent. So for each forward pass, we will pass the entire input vector. So in mini batch gradient descent, we will only pass the batch of the input vector for each iteration. So we will see that in the next part. So this is the basic linear regression. Okay, now we can import a toy dataset and evaluate our model. But before starting that, like, there are a couple of mistakes in our code. One is that it is self.alpha. Another thing is that the variable should be loss, since we have printed the loss variable. So also I will print the loss for every 1000th iteration. Okay, now let us import a toy dataset. So I will just copy paste a code. You can have a look at it. So I have imported the diabetes dataset from scikit-learn datasets. So this is a pre-built dataset that is available from scikit-learn. So here I have also split the dataset into training and testing dataset. Another thing to note is that the data here is already standardized, so you don't need to pass it through a standard scalar. We can directly give it to our model. So now let's create a linear regression object. So iteration we can keep it as 1000. So we have to fit the model with the input vector, which is x train, and output vector, which is y train. Then we have to predict it with the test data set. So we can keep the variable as y prediction. So then we will print the y predicted. Okay, for now we can keep print the loss for every 100th iteration. So I have run the code. So now the model will start to train. Okay, predict. Okay, here you can see the loss is gradually getting reduced. So it started at 29k and it is getting reduced at 4000. So we can run the model for 10,000 iteration. Okay, we will print it for every 1000th iteration. Okay, so here you can see the loss is getting reduced, and we also get a predicted value for the test data set. So what we will now do is that we will use the actual inbuilt library from scikit-learn and then compare our prediction value with the predicted value from the linear regression model from scikit-learn. So from scikit-learn dot linear model import linear regression. So I will just copy paste this code. So the scikit-learn linear regression model uses closed form equation, so it doesn't use gradient descent. Okay, now the predicted value from scikit-learn is here. So you can see the data are more or less similar. 142, here it is 139, 177, it's 179, 141, 134. Here it is 113, 115, 88, 78. So like, one thing to note is our model, we haven't used any regularization. Maybe the data is overfitting. So in future we will use mini batch gradient descent, and we will also use the regularization. Then our model may generalize better. So that's all for current video. Next we can code closed form equation, and then in the third part we will code mini batch gradient descent. So thank you guys.